Thank you for a very nice introduction, and thank you, all of you, for being here. I think I actually have some hint on what happened. That doesn't really. I think it didn't. It wasn't the universe. It was the type gods. You know, because I come from the Erlang world, and we are a dynamically typed language. So I think it was the type gods. They didn't want Lambda World to have an Erlang/Elixir talk, but in the end, I'm here. So we don't need to talk about that any longer. So because the introduction was so nice and won't give you any more details, just a little hint on what I do for teaching and for research, because it's very related to what I'm here to talk about. I teach software architecture, and I use Erlang as a learning vehicle there. Because I want the students to be able to build systems with lots of components and well, lots of nodes, and be able to worry the least possible about memory leaks and about CPUs going skyrocketing. So I found that as a tool, it's very, very easy for them to be able to work with things at scale without worrying about any other details that get in the middle. And I also teach part of a course on software validation. And you might think, how on earth is Erlang fitting on that course? But there's a family of tools dealing with property-based, implementing property-based testing, and Erlang has one of the most powerful one of them nowadays. So that's how Erlang comes in the picture there. And I'm lucky enough so that in my research time, I also work helping or analyzing and studying how functional programming helps industry to tackle very specific problems. And in that case, in the distributed systems world, Erlang plays a very important role. And also how to test this very demanding industry systems. And we also use Erlang in that area. So that's kind of the picture of my background. And so for the purpose of this talk, I really want to give a very slight definition of what I mean by a scalable system, so that we all have the same picture in mind. And it's not that complicated, so to speak. So we think about the scalable system, and we say, OK, I want my system to be able to adapt whenever the workload spikes, and hopefully, most of the time, also to scale down if I don't need any more of those nodes that I have deployed. So we have the upscaling and the downscaling. And of course, you could say there's always the money-based approach. So if I need more power, I buy a larger machine, and I deploy my system in that larger machine. But then the downscale doesn't really work that much. You may have your very large machine sitting there, not really being exploited to the fullest most of the time. So in terms of upscaling and downscaling and dynamically adapting, it's more interesting to be not the vertical scaling, but the horizontal. So we deploy copies of your system in different nodes, and they all transparently serve your clients without further ado. So if we could say which are the main properties that enable or that allow systems to fit in this scalability box, so to say, I would remark 3 of them. It's not an exhaustive list. You're free to disagree. But these are my 3 highlights for this talk. So first of all, I would say you really need to focus on modeling your business logic in the shape of really small independent tasks. Because if your system has like 2, 3 really big, complex jobs to do, then it's going to be really, really hard to make it highly scalable. So once you do that, or for doing that, one of the things that you want to do is to get rid of as much as management logic as you want, error management logic. So to make your tasks really specific, really small, really focused, you get rid of the error handling, and you outsource that to other parts of your business. So you have your really tiny, very focused business logic, and then you have your supervision tasks. So you will have other components that will supervise those, or that will monitor them and be aware if they're healthy, if they need to be restarted, if you need more of them, if you need less of them. So you separate those honoring the first principle and then implementing the second one. And those two combined will make it easier for you to comply with the third one, which is like the mantra of any highly scalable distributed system. So don't have a single point of failure. So we can have those as requirements. And then to make this like visible, we can mention a few systems that have these properties and that, as you may suspect, they have something else in common. So one example are advertising systems. So in case you don't know how this industry works nowadays, so back in the day, you would you want to print an ad in your village newspaper. You go to the newspaper, you buy the Sunday page, and you play something, and then on Sunday your ad is on that web page. But this is 2019, so ads are shown to us mostly when we browse the BBC website or Facebook or Instagram or whatever. And when we are loading that page, there are lots and lots of tiny spaces where ads are going to be shown. So in that very, very small amount of time that a space is going to be ready to be shown to you, someone is going to bid for that space. So there are lots of companies that have lots of products that they want to be shown to you, but they don't bid directly for those. Companies like AdRoll act as an intermediary, so they have the product owners as clients, and they bid for the spaces, and so they know how much the clients want to bid, how many ads they want to show, and where, and the demographics, and all that stuff. So in microseconds, they are able to bid and actually serve the ad that you eventually see. So that's a really highly distributed and scalable system, an example of that. Another typical systems that fall in this category are payment gateways. So think, in this case, it's MasterCard, but think any major credit card, have millions of clients all around the globe. Any moment, any time, there are purchases waiting to be authorized. So there's, again, this dynamic load that's growing, going down, and there's small, very focused, very specific tasks. It's not a large amount of business logic. That's something really, really specific. Then on a more fun side of life, if you will, we also have the gaming industry. They also have a lot of requirements that fall in this category, but in this case, I will mention specifically, if you're familiar with League of Legends by Nintendo, well, there's as many other online games. They have a chat where the users can, well, just chat along as they play or organize, come up with strategies or whatever use they want to have for that chat that comes with the game. And then there are other social networks, and there's also Bet365, which is a company that, in their case, well, the scalability of the system, well, has kind of matched when there's a sport event. So they kind of could predict when their scalability is going to be put to the test. But again, it's kind of, again, very small, specific tasks and the need of monitoring so that nothing fails or what, those sorts of things. And on top of this, I'm going to put WhatsApp. And I'm not going to explain to you what WhatsApp is, because probably most of you use it. And by now, you probably guessed what all these systems have in common. And it's their backends are implemented with one very successful secret ingredient, which is, of course, Erlang. Surprise. So if we could, again, as we did with the scalable systems, if we could define in 4 very simple lines what makes Erlang the perfect secret ingredient for these sort of systems, well, I've tried to summarize them there. So it's a functional language, yes, but we tend to focus more on the concurrency-oriented part of the language. So the properties make it such a good fit for these kinds of problems that we're talking about start with the fact that creating and destroying processes in this language is very cheap. So yeah, a functional language, everything is a function. But Erlang goes one step beyond and say, okay, you have everything as a function, but have every function run in its own process. Okay? So for that to be actually feasible, those processes need to be really cheap to create and destroy, because you're going to start processes, execute function, the function ends, the process dies, and it starts again and again. And well, this is possible because Erlang runs in a virtual machine that separates the idea of your Erlang processes from the OS processes. Of course, creating threads at the OS level, that's expensive. But the virtual machine in the middle makes a very good job in separating that, in having different processes running in each OS thread in a way that they don't interact with each other, of course. There's transparency, and there's isolation, everything that we love about the functional world. But then there's also a very efficient job in scheduling all those processes so that your machine can hold tens and hundreds of thousands of them. So that's one of the things that will make easy in these systems to have really those independent tasks that we were talking about. Well, as I was saying, they are isolated, and the only way how this isolation materializes is that well, processes communicate with each other via message patching. So you will send a message to a process, and it will stay there in its inbox until the process decides how and when to react to that message, if ever. So that's one thing. Then, since everything is a function and every function should be running its own process, well, as I was saying before, that is also true for the monitoring part of your logic. So you will have processes monitoring other processes in a very natural way. Then, since processes are very cheap to create and to destroy, and one last piece of information that you need is that in order to be able to send a message to a process, the only thing you need to know is the process identifier. And this means that you may have a number of virtual machines running, we call them nodes, in the same box or in different physical boxes. And for you as a programmer, to send a message to one process or to a process that is on your same node, and sending a message to a process that is in a different Erlang node is transparent. So there's no difference in the code that you will write. And you could be oblivious of that process being local or being remote in that regard. And of course, that has an impact on the way how you think and how you communicate your processes, because asynchronicity is natural and distribution comes naturally in that mental picture. So it reinforces the idea that tasks are isolated and that communication needs to comply to these headlines. So it kind of naturally helps you to avoid those single point of failures that we were discussing. So that's kind of the formal picture or the theoretical picture. So let's see an example that will help us see how we can grow from one simple idea to something that we could call scalable. So for this purpose, I've used this kind of a typical example in the Erlang world, an echo server. So you can think of an echo server as a process. We could implement it as a process that will just be there waiting for your messages as a client, and it will just bounce your message back to you. It's a very simple idea, but then you can think that instead of just bouncing the same message, the echo server could be doing something with your message before replying it back, and then instead of an echo server, it will be something else. So, well, I've pictured here your administrator just to highlight that someone will start and stop the server, and then every one person or other process will send messages and get the replies. So that's a very simple idea. So in most cases, I would show you here some Erlang code. But you know, I was preparing this talk a few weeks ago, and I would say, you come to a technical conference, you see lots and lots of code, so I'm going to take a different approach. I won't show you a single line of Erlang code, but I want you my challenge is that you want to look at the Erlang code that I've written to run these examples. So let's see if I manage. So how many lines of code do you think I wrote for this piece of software? Dozens, 10, did I 10, 20? Or one world. You were in the Kotlin the Kotlin talk this morning. Well, you're really rather optimistic. It's also a bit more. It was 35. Okay, not bad, not bad. It was kind of in the same range. So with 35 lines of code, you have a robust Erlang process that will comply with this idea. But of course, this is not really scalable, right? I mean, yeah, it's a very tiny task, isolated, but it has no monitoring. It has no, well, it's clearly a single point of failure. So the first step that we will make to evolve this would be to add supervision. And in Erlang, it's part of the languages, part of the default, the standard libraries. The supervision is part of the standard libraries. So see that I've changed here from process to gen server, which is an abstraction that comes with Erlang. That it will implement a lot of the logic that comes with starting process, registering it with a name, and listening to messages and stuff, and also add the links to another kind of process that will play the role of supervisor. So say that you declare your module as a gen server and you declare another module as supervisor, and you have to fill in a few gaps, but there's a lot of boilerplate that you inherit. So I've changed also this a bit because your admin will no longer start directly the echo server. They will, of course, start the supervisor, and the supervisor in turn will start the echo server, and will just, its only role is to be sure that the echo server is always there no matter what. So the question still stands. How many lines of code do you think I now have here? Oh, oops, sorry, spoiler. Okay. So, well, it grows a little bit. So we go from 35 to 88 here. This is because you have to implement a lot of code, but some of them you won't use for a really small example like this, but still you have to fill in. And then your supervisor is almost as tiny as the process, the echo process was when it was on its own. So, well, together we have like 120 lines of code, and we now have a supervised process. So if this process, whatever happens to it, I might want to kill it 1,000 times, and 1,000 times the supervisor will bring it up again, if configured to do so, of course. But again, this is very nice. At least we have separated the very specific task of replying to the client, the very specific task of monitoring other process, but still we do have 2 single point of failures in this case. So we want to get better. Next evolution will be, well, now that I have a supervisor, why make it supervise only one process? I can supervise any number of siblings here. So, well, this seems like a small change. How many lines of code do you think I have here? So it was, for context, it was 88 and 34. And now it's 87, actually. We have 1 less line of code for the echo server, and 37. And that's because I automatically generate names for this. So now they don't need to take care of their own name. It's a supervisor that here generates names for the kids, for the children, before starting them. So that's OK. We've removed the single point of failure from the echo server side. We now have as many as we want. But we still have here 1 single point of failure. So how do we get rid of this one? And the answer is horizontal scalability. So now we have a system that we can deploy as many times as we want in as many different Erlang nodes as we want. So this would be the picture. Now we have a number of echo servers, each of them in its own supervision tree, but if anything happens to this supervisor and it's no longer capable of restarting its children, then, well, we have a sibling, or, well, here there's 2, but we could have as many as we want, or as many as we can fit in our hardware, so to say. Last question I assure you, it's the last time I'm going to ask. But how many lines of code do you think we change from here to here? That's right. Because as I said earlier, there's no difference from the developer point of view from when you're just communicating with processes in your own node as if they are in different nodes. So in this case, they're not really communicating. The clients would be communicating with eco servers here or in a different node, but it will be transparent for them. The code is the same, and there's nothing you need to change here or nothing you need to change here. Once you are here, then you can move to here if you've done things properly. So perfect. So we've used Erlang, we've used the secret ingredient, and we are happy, and we are early, and we can have another coffee, right? Because you're all going to take my word for it. No? Yeah, OK. Then we're going to test it. You asked for it. And if you were in Adam's workshop yesterday, this will very nicely fit in what he was saying, but I will remind what traditional testing would be. So in a system like this, well, in any system actually, if you don't think much further, you will go ahead and start designing test cases, right? So for a system like the eco server, we would say something like, OK, let's start the server. And then we will send some message, and wait to receive it, and we check, in this case, if the message is the same one, and then we will stop the server. That's the sequence. So from this design, then we will say, OK, I'm going to send different kinds of messages. Some will be empty, some will be very large, some will have like special characters, you name it. So you design your input data. And from one text design, you have a number of instances of test cases. Of course, sometimes this means that depending on what you're sending, you will be checking different things. Not in the case of the eco server, because it's really simple. We just want the same reply that we just sent. But in a more sophisticated server, this may have some implications. So depending on what you've sent here, you check different things, or depending on your history, and we will come back to that idea. But in traditional testing, you would just do this. And of course, at the very least, you will automate this somehow so that this is executed every time you have changes on your code base. And if you're like really, I don't know, worried about quality, you probably would measure test coverage. And I can assure you, this test case will give you 100% coverage of the eco server. Would you be happy about that? If I run this test with a few different messages, would you be happy? Will the system be scalable then? We've tested. We have 100% code coverage. Right? OK. So how do we do it with property-based testing? The properties that we were seeing yesterday during Adam's workshop were mostly like library-like properties, so didn't really they didn't have to do with a stateful thing. He mentioned at the end, we can extract this idea from like lists that we reason about the length or the content or the isomorphic properties and blah, blah. But we can do that the same for stateful entities. And that's right. So when you're dealing with a stateful entity, and a server is most likely to be a stateful entity, even if in the case of the eco server is not, it's a slight difference. So the property would be one unique property, and I will tell you that in a minute. And the steps are the following. So first, you will say, I want to test something, like from a black box point of view. I don't want to see, I don't know what's inside the eco server. I know the things I can do with the eco server. I can start it, I can stop it, and I can send messages to it. Perfect. Then you may want to specify preconditions, and those will like restrict the kind of sequences of these operations that you will have as part of your tests. And say that you want to say, no, the second time I start the eco server, I want to see an error, or the second time I've stopped, the server is already stopped, I want to see an error, or if I send a message and the server is not up yet, then I want to see certain error. So those will kind of filter then less interesting tests. Then, of course, you will have to generate your input data, and now I stress generate. I don't want to pick it. As Adam was saying yesterday, I don't want to think about, I've included the empty message, I've included a message with empty spaces, with non-UTF characters. I don't want to think about that. I want to say, my messages are strings, and I want to use a string generator that comes with the tool. And of course, if I have something more complex than a string, well, I will use generators to create my custom generator for lists of tuples, that the first element is an integer that is greater than a certain value, and the second element is a list that has binaries and blah, blah, blah. So you can compose the basic generators to virtually generate whatever you need. And last but not least, you will specify the post condition. And this is actually what you expect to see when there's a sequence that you have created using your API definition and following the preconditions and using the generators, then you expect to see something when this is executed. So in this case, it will be, well, I want every time I call echo, I want to get the same string back. If it were more complex, the post condition will be also equally complex. But we can talk about that later if you want. Just for the time being, I hope this conveys the idea of the steps to build the test specification for property-based testing when you have a stateful entity. And then the property, what we call the property in this case, is that no matter how, for all, if you remember from yesterday, for all sequences that I can automatically generate using this specification, I want the post conditions to hold every time. In other words, if I generate sequences, if the tool generates sequences, and at any point any post condition is violated, that is a counterexample. That is my failing sequence. That's what I will use to debug my implementation. And of course, this can be automated and integrated with your CI systems and blah, blah. And trust me, this gives you much better quality than the 100% code coverage. But by now, I don't expect you to take my word for it, so let's see. So for the smallest example, right? Just the eco server. With the specification that I've talked about right now, in my laptop, which is a really modest machine, you can run 1 million test cases in less than an hour. Less than an hour. And the test cases, what do they look like? They are sequences like this one. This is one of them. There will be shorter sequences and larger sequences. But this is one of them. So I start the server, send a message, stop it, send a message, start it, send, start, send, start. And for 1 million like this, I'm checking. Well, I don't know about you, but this gives me far more confidence than any 100% quality measure or coverage measure. And that's the bonus part. How large is that specification? How large is this for the eco server example? Well, it's 61 lines of code. 61 lines of Erlang code, actually. To specify your operation, to specify your preconditions, to specify your postconditions. And with 61 lines of code, you get this. OK. What about the supervised eco server? Well, in that case, remember, we were no longer starting the eco server manually. It was we started the supervisor, and the supervisor will keep the server alive no matter what. So the API changes a little bit. I just don't start it anymore. It starts when the tests start. So I just send messages, and at some point I decide to kill it. So I have like an artificial operation in that API for test purposes that kills the process. So an example of this sequence in this case would be, okay, you send message, send, you kill it, you send, you kill it, you send, you send, you kill it, you send. And this works if by the time I'm doing send, the echo server is up and running again. So the supervisor has properly done his job. And again, this is a test sample. It will be shorter sequences, there will be much larger sequences. And you get, in this case, well, there's some time to kill and recover from the kills, but you still get 100 or can get 100,000 tests in a little bit over an hour. For how much code? One less line than before, actually. 60 lines of code. So the specification here, because it has one operation less, we never stop it, and we never started, we just kill it, so it's slightly one line of code less. Following step, the supervisor with lots of children. So we change now the API again a little bit, the specification, the test specification a little bit. We now will start, but we will randomly generate how many children the supervisor is going to start for each test sequence. So we will start with 5 children, we will message the first, we'll message the fourth, we'll message the first, we'll message the third, we will kill the fifth, then we will kill the second, we will message the second, we will kill the second again. You see how I work with this. Again, this is one example of test sequence. These numbers are randomly picked. So each sequence, longer or shorter, will have different numbers every time. And with 72 lines of code, you get 100,000 tests in about 2 hours. Nice, huh? Nice. Last example, with the nodes. Now, I could have done the example to have an arbitrary number of nodes, but since my laptop is a 4-core, I just fixed it just for 4 cores. And so the API again changes a little bit because I want to randomly start supervisors in each node with different number of children. So an example of the sequence would go like this. We start in node Alice, a supervisor with 2 children. Then we kill the children number 8 in Carol. Okay, it was not bad anyway. We start in Bob a supervisor with 9 echo servers. We start in Carol a supervisor with 13 echo servers. We send a message to the 3rd kid of Carol. We kill the 3rd children of Bob, blah, blah, blah. You see how this goes. And again, this is where the orders of magnitudes go. Well, they go down for obvious reasons, but still, you can get 10,000 tests in this kind of machine in roughly an hour and a half. For 102. Oh, we crossed the 100-line barrier, but we're still there. So it's really, the specification is really, really tiny, as is the Erlang code that we use to implement this. So it's really, really hard to beat. So, are we happy now? I'm rather happy. I mean, we could still grow this example because we've been like stressing the part of the server, but we would like to have like random number of clients concurrently load testing or implementation. But I think I can leave it here, and as I say to my students, the next step you can do as an exercise. And you're most welcome to come and talk to me after that. So the last question is, okay, this is a very nice academic-like example. You've conducted us from the very small example to something that is growing, and yeah, we're pretty much convinced. But how does it look in real life? Do people from those companies do things similarly? Well, I don't know if they do, because I haven't worked with them, but the companies we work with at the University of A Coruña, we run some products with local companies that want to start using this kind of technology and help them through that. The most recent of which is a system called Ethic that is mostly a SCADA system. If you've never heard about SCADA system before, well, if you think of IoT devices, say temperature sensors or humidity sensors, any kind of sensor that you can think of, so this company will have a number of installations with rather high number of sensors in each one, and they wanted to have like a control panel where they could see the status of the installations, and if a sensor is giving some measure and check it out on, or ask the sensor to perform some additional measures, that sort of thing. So this would be like the high-level view of that system, where this is the backend, and these are all the sensors that you have there, and they have like the regular user and the technicians, and that means so. I know you're not going to see the details. I just want you to see the shape. So this is the shape of that backend, the shape of the supervision tree that we built to take care of all the different tasks that compose that system. And I will not show you the code in this case because I can't, but the same techniques that we've used and I've conducted you through this talk on how we test the eco server, they apply to this kind of system. And the same ratio between the effort that you put in the original code and the effort that you put on the test code to get that kind of security still stands. It's correlated. So, OK. Let's see if I succeeded in my own challenge. How many of you would like to pick at this Erlang code? Great, so now you can do it. I will post the slides later on, but all the code in the different versions of the Erlang ecoserver that we've seen, and all the test modules that I've run with the measures that you've seen are there. And it's all very well documented, and if you find anything that you don't understand or you want some explanation, you can talk to me about that. You can contact me. So what I would like to take home, apart from the urge to look at that Erlang code, is just very specific things. So scalability starts from the moment that you start thinking how your system is going to be, what your tasks are going to be, who is going to monitor what, and the fact that you separate explicitly your business logic from your monitoring logic, as we will be seeing. But of course, that's not enough. I mean, you may use Erlang, and you may be confident or not. In order to at least empirically validate what you think of your system, you need to test it. The good thing, the good take-home news is that Erlang is strategic at this moment in time in this regard, because we have both like a very powerful language that was exactly born for this kind of systems, and also the most powerful tools from the PBT family are implemented in Erlang. So they were born in the Haskell family, but the ones that we have in Erlang, they are the most expressive and the most powerful, to the best of my knowledge. I've used the one, I mean, almost every language has a PBT tool nowadays. I've used the Python one, the Java one, that have a number of them. And I can tell you, I would ask you to take my word for this in this case. They still have to match the power of the PBT tools in Erlang. So, and in case you wonder, you come from a company and you say, OK, I would like to try. How visible is the Erlang community? It wasn't as visible in the years back, so there were lots of companies using Erlang, but they didn't know each other. There was not a community of companies using Erlang, but it exists now. A few months ago, the Erlang Ecosystem Foundation was found, and there are a number of companies that are very vocal now about, hey, we use Erlang for our systems, and we want to spread the word. So this is a very powerful technology for this particular kind of problem. And well, I'm part of the education working group here, so if you're interested of knowing more about the foundation, you can come later on, find me, and we can talk about that. And that's it. So I hope you will eventually use Erlang. Thank you.